Our next speaker is Ashwin Pananjady. He is a PhD candidate at UC Berkeley and a Swiss Re Research Fellow in the Probability Program.
All right, thanks, Prasad. Hopefully you can hear me. Awesome. So in case just one picture wasn't enough, there's another picture on the slide. So I'll be joining Georgia Tech next year. And my PhD at Berkeley was, among other things, on automatic adaptation to structure in high-dimensional estimation problems. So today what I'll tell you a little bit about is what that perspective has to bring to reinforcement learning. And this is important at a high level, both in theory and practice, because lots of the worst case theory we have in reinforcement learning can often be extremely pessimistic. And secondly, some notion of the intrinsic difficulty of problems is helpful also in algorithm development, because multiple algorithms may be optimal in the worst case, and then you may see differences as you zoom in. So this is based on joint work with a variety of wonderful collaborators at Berkeley. Next slide. So the particular thing that I want to tell you about today is policy evaluation, which is this extremely simple problem of solving a linear system. It's evaluating what's called the value function of a Markov reward process. So the Markov reward process is given by some tuple PNR, a transition matrix, and a reward function. And you want to find the value function, which is given by the solution to that equation in the middle. So what we'll operate in today is this model called the simulator, or the generative model, where you just get IID samples from this pair and you have to evaluate the value function. Next slide. So there are a variety of concrete algorithms you might think of that work with these samples. I don't expect you to read the math here, but many of them are very, very natural, right from what's called the plug-in estimator in statistics to others based on stochastic approximation. So typically, you don't just do this in the ambient space. Next slide. You do this in what's called the function approximation setting, where you also have some subspace, typically denoted there by the phi quantity, and you run exactly the same algorithms with projections onto these subspaces. So these go with a variety of names in the temporal difference learning family. What might you like? Next slide. You might like estimates, right, that satisfy a guarantee like in the bottom. So this is what would be called an oracle inequality in statistics. You want some guarantee on the approximation error, how far you are from the best approximation within the subspace, up to some additive statistical error, capturing noise in the problem. And that's going to guide our development today in this instance-dependent fashion. So in the next 30 seconds, let me tell you a little bit about each of those, starting with the statistical error, epsilon n. Next slide. So here I'm going to use something to parameterize instances. The details are unimportant, except to see that I can actually vary the difficulty of the problem here on the x-axis by simply varying the discount factor gamma. Next slide. And what you'll see is if you plot the behavior of many of the algorithms that I talked about on the previous slide, you actually see a distinct difference. All of these algorithms are worst case optimal in a certain sense, but when you plot it with the difficulty of the problem, in particular this effective horizon, you see a separation. The temporal difference learning algorithms are distinctly suboptimal, whereas the plug-in algorithm is in fact optimal as compared to a lower bound, which is information theoretic. The stochastic approximation algorithms can also be improved with a variance reduction device to make them optimal. Next slide. This brings us to the approximation error, the factor that sits outside the minimum possible error. And classical results have known that you can upper bound this approximation error by something that depends on the discount factor. It grows as the discount factor goes to 1. What we show, next slide, is that the story is significantly more nuanced. As you look at the ambient dimension of the problem, what you can show is an instance-dependent characterization now that provides both upper and lower bounds, showing that these algorithms are optimal in certain regimes, but suboptimal in others. Next slide, and this should conclude. Although I said this for a very specific setting, there are consequences for more broad settings in reinforcement learning as well. Thank you.